Okay, here we are in assignment 9. Question 1 is answered by just reading the textbook. So take a look at the textbook. It's in the resource section, first section of Moodle, and you'll be able to answer these questions. Question 2 is about the 3 right-hand rules, 1, 2, and 3. They're explained in the introduction video. But just briefly, right-hand rule number 1 relates the force on either a moving charge or a current-carrying wire passing through a magnetic field. So the finger is the direction of motion of the charge, the bent fingers point in the direction of the field, and the thumb points in the direction of the current. And problems 3 through 6, I think, are applications of right-hand rule number 1. Right-hand rule number 2, the thumb is in the direction of the current through a wire, and the fingers curl in the direction of the field. And the field around a current-carrying wire forms closed loops, circles, where the field gets weaker as you move away from the wire. And if we take a straight wire and wrap it into a coil, then the current is circular and the field inside the wire is straight. So we have a third rule, right-hand rule number 3, where the fingers curl in the direction of the current and the thumb points in the direction of the field inside the coil. So field lines pass through the coil in this direction, leave from the North Pole, circle around, and pass in through the South Pole. The South Pole of a coil is where the field lines enter. The North Pole is where the field lines exit. So problem number 3, 4, 5, 6, 7, and 8 are all applications of right-hand rule number 1. So let's do one together. Here, figure C shows the force, shows the direction of the force on a current-carrying wire, I, not shown. The direction of the magnetic field is shown. What is the direction of the current in the wire, not shown? The direction is, so remember, in this case, we're going to point our thumb in the direction of the force, our bent fingers into the screen, into the page, in the direction of the field, and the index finger then would point in the third direction. You'll see when you do that, your index finger is pointing up, so the current is up. Moving on, we see that number 9, 10, and 11 are a bunch of statements, true or false statements. 12, where you have to pick the correct statement. That's all covered in the general video, all the properties of charges in magnetic fields and the properties of magnets. So I'm not going to comment on those. Let's go to 13, and we'll talk about 13. So in problem 13, read through it. I added a little note about the video labeled Fall 2020 video. Between minute 7 and minute 13:30, I discuss what I'm going to talk about briefly now. And here's a hint that I'll also talk about. So when a charge moves into a magnetic field, let's say we have a magnetic field going into the page, and the alpha particle is a particle with a charge of +2 times 1.6 times 10 to the minus 19 coulombs, right, times 2. There are 2 protons. So I'll draw the alpha particle. when it enters the magnetic field, if it's, say, going along the x-axis, and the field is into the board, we use right-hand rule number 1. I point my finger along the x-axis, my bent fingers point into the page, and my thumb points up. So that means there's going to be a force on the positive particle up, and as long as it stays in the field, it will continue to move in a circle at a constant speed, bending. So I'm not going to discuss this in detail right now. If it were a negative charge, of course, it's going to go the opposite way. It's going to move in a circle this way. And so the force on the particle is QVB sine theta, but the direction of the particle is perpendicular to the field, so the sine of 90 is 1. So QVB, the force, is going to be equal to the mass times the acceleration, and the acceleration is v squared over r because it's moving its uniform circular motion. So that's all what we learned last semester. So the sine of theta becomes 1. There's a v here, there's a v squared here, so it cancels one of those two v's. And so we're left with the equation QB equals mv over r, and it's the v we want, right? We're trying to calculate the speed of the particle here. So the velocity, do the algebra, don't wait for me. The velocity is going to be QB r over m. And the b and the r and the q and the m are all given. Remember, q, the alpha particle, is 2 times 1.6 times 10 to the minus 19 coulombs, right? The charge on a proton is the same as that of an electron. So that'll give you v, and then once you have v, the kinetic energy is simply 1/2 mv squared. And the conversion from joules to electron volts is 1 electron volt is 1.6, this is in your equation sheet, times 10 to the minus 19 joules. And it asks for it in mega electron volts, and mega is 10 to the 6th. So you have to make that adjustment. Oh, actually, that's all given down here anyway. So number 14 is much like 13, only in this case we're given the energy in MeV, so that's 4.94 times 10 to the 6th EVs, and you have to do a units conversion to get joules. And once you have joules, you can get the velocity, right? Kinetic energy is 1/2 mv squared, so you just have to solve for v. And make sure you have to have joules because that will give you meters per second. And when an alpha particle enters a magnetic field, which is given, the force is just QVB sine theta, but it's entering perpendicular to the field. So you can calculate that. How do I know it's perpendicular? Because the velocity is along the positive x-axis and the field is in the j-hat or y-axis direction. And the path of the alpha particle will be a circle because that's the way particles in a uniform field move. Why? Because the force is always perpendicular to the velocity vector. And the radius, you just go back to our equation, remember from last time, QB equals mv over r. And in this case, we want r, right? We're asked for the radius. So if we solve this for r, go ahead, do it. R equals what? Just algebra, mv over qb. Just make sure you use the right units for all that. So 15 should be straightforward, right? The force equals IL cross B, or ILB sine theta. You can see that the wire is along x and the field is down along y, so theta is 90 degrees. And the I is given, the B is given, and the L is what? The length of the wire in the field. So you have the length of the wire in the field is shown in the figure. It's 12 centimeters, but make sure that you use the right units. And the direction is given by right-hand rule number 1. You've had lots of practice with that. Point your thumb along the x-axis, your bent fingers, the field pointing down. I get it wrong. Point your index finger along the x-axis in the direction of the current. Your bent fingers pointing down along the y-axis, and your thumb should go into the page. So that would be along negative k at. Okay, problem number 16. So read through the thing carefully and notice the way in which it's the same and different from what we did in lab. That's all described in the write-up. So we want the field from wire 1 at the location of wire 2. So wire 1 carries a current 2.33 amps in the I-hat direction. Wire 2 is at a position of 1.25 millimeters above it. So we want to get the field at wire 2 due to wire 1, and using right-hand rule number 2, pointing my thumb along the wire, I can see my fingers coming out of the page. So the direction of the field is going to be out of the page, and we will use B equals mu naught I, that's I in the wire, so that's I1 because we're getting B1 at this location 1.25 centimeters above it, and so 2 pi A is the distance from the wire to the point, and that's the 1.25 millimeters. So just make sure you get all the units right. To get B, you have to change the millimeters to meters. And mu naught is a given quantity. And now, next question is calculate the magnitude and direction of the magnetic force on the wire. So this is the field. So the force on the wire is going to be ILB sine theta. But since the current in wire 2 is also in the I-hat direction, and the field is coming out of the page, if we use right-hand rule number 1, this is the force rule, right? So I point my index finger in the direction of the current. I have to point my fingers coming out of the screen. You got to turn your hand, and how does my thumb point? My thumb points down. Make sure you can follow that. So the force is down. this makes sense, right? In lab, the currents were the opposite direction, and they moved away from each other. So if the currents are in the same direction, the wire is going to move towards the other wire. It's going to be attracted. So the force is down, and the direction of the current and the field are perpendicular, so the sine of theta is 1. And the I, this is the force on wire 2, so you've got to use the current in wire 2, and the length of the two wires is given. And so we have the field goes here, and that will give us the force on that wire and the direction. Okay, I think that's enough to let you finish the problem. Okay, read the instructions carefully. You have 4 wire segments in a field in the I-hat, x-axis direction. The field fills the space. The value is given in millitesla, so make sure that you change that to Tesla. And the length of the wire is given in centimeters. Make sure you get the units right. And so the force on each wire is going to be QVB, ILB sine theta. And so there are 2 different lengths, so make sure you get the right length. And pay attention to what theta is. So for segment 1, the current is this way and the field is in the opposite direction. So that's what? 180 degrees, and the sine of 180 equals 0. And segment 3 is in the same direction as the field. So those 2 segments will have no force on them because they're parallel or anti-parallel to the field. Segment 2 and segment 4 are perpendicular to the field, so that will have a sine of 90 or 1. The length of the wire is given, the field is given, and the current in the wire is given. And all you got to do is use right-hand rule number 1 to predict the direction of the force, and you might guess number 2, the current's going down. If I point my index finger down and point my bent fingers in the direction of the field, my thumb comes out of the page. So the force is coming out of the page along positive K, and for number 4, better be the opposite. Your thumb points into the page. And so you see, if we put a vertical axis through here, this coil is going to spin around that axis because the force is equal but in opposite directions. And so there's a net torque. So just remember, torque equals R cross F, or R F sine theta. And so you get a torque when the angle's 90 degrees. And the R is the distance from the axis to the force. So what is that? That's half the length of that upper wire. And there are 2 torques, right? There's the torque because of wire 2 and the torque because of wire 4. So make sure you do the summation of the torques. Okay, read through all this carefully, and I can discuss it with you. So if we have a positive particle coming from the source and moving down, as it enters the electric field, it's going to have a force in the negative, along the negative x-axis, negative I-hat direction this way, because a positive particle moves in the direction of the field. It's repelled by the positive plate. But a positive particle coming into a field, use right-hand rule number 1, point your index finger down, your bent fingers into the page, your thumb is going to point in the opposite direction. So there's an electric force and a magnetic force which are opposed to each other. And so there's going to be a force, an electric force, and a magnetic force in opposite directions. And so if the magnitude of those two forces are equal, they'll cancel each other out. And the electric force is just the charge times the field. And the magnetic force is the QVB sine theta, but just QVB, right? Because the sine of theta, since the field and the direction of the particle are perpendicular, sine of theta will be 1. And so if the force due to the electric field is stronger, the particle will move in the direction of the field and not pass through this device called a velocity selector. If the magnetic field is stronger, then the charge will bend this way and it won't get through. But if these two are exactly equal, the particle will pass right through into the magnetic field, where it then bends in a circle according to the equation that we have used many times, and that's QB equals mv over r that we derived earlier. And so notice that Q is on both sides of the equation. So if we have a velocity where the electric field, with the ratio, if the velocity is equal to the ratio of electric field to magnetic field, then a particle of that velocity will have equal and opposite forces. So a velocity lower than that will weaken the magnetic force and the electric force will eliminate it. If the velocity is bigger than this value, then the magnetic force would be bigger, and in either case the particle won't get through. It'll only get through if the velocity is exactly equal to that, and that's why this device is called a velocity selector. Now when it comes in, it bends in this direction. That tells us from right-hand rule number 1 that it must be a positive charge, because if it were a negative charge, it would bend the opposite way and move in a circle in the opposite direction. And so you can use this equation to solve the rest of the problem. That's it. Here's the table of contents at the end, because I don't know what it is in the beginning and I don't know how to preload it to the front. So here it is.